Welcome back to ECE 442-542. We're still looking at lecture 5.2, but now let's go ahead and look at what happens when we try to combine two of these different design specifications. We've looked at the three different design specifications: settling time leading to concentric circles. The faster the response, the smaller the circle. We've looked at percent overshoot. Those are the logarithmic spirals or the heart shapes, and the smaller the heart, the faster or the less overshoot that we have. And finally, the third design specification was the time to peak, or the peak time, and there that led to wedges, which a larger angle or a larger wedge gave us a system that peaked more quickly. Let's now look at what happens when we combine a settling time specification and a percent overshoot specification and try to solve those or satisfy those two design specifications simultaneously. What do we know about T-settling? We know that that leads to circles, so now we're thinking about radii or radius, r, and percent overshoot gives rise to damping ratio, which is this zeta value. Or here we have circles for T-settling, and for the percent overshoot we have hearts. Or we now are looking at circles, with the smaller circle being the system corresponding to a system that has a faster settling time, or T-settle is smaller. With respect to these hearts, we could now, the unit circle is going to be a zeta value of 0. If we have a bigger zeta value, then we have a smaller heart shape, and so now the smaller heart shape corresponds to a zeta value that's bigger. We want to now try to obtain a pair of complex conjugate pole pairs Z that satisfy a settling time specification and a percent overshoot specification simultaneously. So where are the poles going to be? And hopefully you can see that we could draw a circle, and then we could draw a logarithmic spiral, and their intersection would actually be the location that would give rise to this z sub delta. So given an r and a zeta, we could, if we could accurately draw the circle and the logarithmic spiral, the circle corresponding to a particular r for a settling time specification, the damping ratio zeta, the logarithmic spiral corresponding to a percent overshoot specification, we could find graphically their intersection. But my graphing skills might be a little bit limited, so can we actually find a numerical value for z sub delta once somebody specifies an r and a zeta? Or can we translate r and zeta into an r? That should be easy enough. Since we're given r, we can find the amplitude or the radius of the circle. But now we want to now specify theta sub d in terms of r and zeta, and not in terms of, because nobody gave us a peak time, so they didn't explicitly provide us with an angle theta sub d. So what is this angle theta sub d? Remember, z is e to the st, and we can parameterize s as minus zeta omega sub n plus j omega sub n square root of 1 minus zeta squared. We distribute the t across both of those terms, and now we're left with this piece being our r value, or the radius, and this piece being our angle theta sub d. Where if we wanted to even get a little bit more detailed, here is our sigma, and this, well, this piece and this piece, maybe I should just do it up above here, is our omega sub d. Since I've already squeezed the sampling period t in between the omega sub n, the natural frequency, and the square root of 1 minus zeta squared, it's maybe unclear what that is, but this is now our omega sub d t value. That's theta sub d. So now we have r is e to the minus zeta omega sub nt. Here is our sigma. We can now, what we're trying to do is we're given zeta and we're given r, and t will be given. So now we have one equation and one unknown, and that one unknown is omega sub n. Can we now solve for that? Or, in fact, if we look at this particular angle, theta sub d, it also contains an omega sub nt. So maybe if we can solve this r expression for omega sub nt, we can substitute it in to our angle expression theta sub d, and theta sub d now will be a function of r and zeta and not a function of omega sub n. That's where we're headed. So now if we take the logarithm, natural logarithm of both sides, we have natural log of r is now minus zeta omega sub nt. And this is what we're trying to isolate. Or we can now find that omega sub nt is in fact the natural log of r divided by minus zeta. Or we can pull that minus sign more directly out in front, and now we can replace omega sub nt in our theta sub d expression with this expression that only involves r and zeta. Remember, omega sub d was this omega sub n square root of 1 minus zeta squared, and that's times t. We can now pull the t into a different location of that expression, and now you can see that omega sub nt is right there. That's theta sub d, but we already have an expression for omega sub nt in terms of r and zeta. So if we plug that in here, that's omega sub nt times the square root of 1 minus zeta squared. Now we do have an expression for theta sub d, this angle in our polar structural form of z sub delta. R was given by the settling time, and now we have specified or parameterized theta sub d, the angle of that pole location, in terms of the radius and the damping ratio zeta. So if somebody gives us percent overshoot and settling time, now we can translate that into a particular pole location in the complex z-plane where r is explicitly given and theta sub d is now in this structural form or parameterized form in terms of r and zeta. And so theta sub d is derived from r and zeta. That now is how we could combine these different performance specifications to arrive at a set of poles that satisfy simultaneously a settling time specification and a percent overshoot specification.